Batteries do not fail because they are misused. They fail because they are used exactly as intended. Every time energy is stored, a slow process of damage begins. Not dramatic, not visible, but permanent. This is not a story about failure by accident. It is about a system engineered to fail slowly so it can work at all. Batteries sit quietly inside phones, cars, and power systems, doing their job without drawing attention. They are treated as finished objects, not as processes unfolding over time. We trust batteries because they appear sealed, contained, and predictable. Once installed, they seem to disappear from concern. Unlike engines or moving machines, batteries give no sound or motion to warn us. Their silence is interpreted as stability. This trust allows batteries to become infrastructure. They are expected to work continuously, invisibly supporting modern systems. Because nothing seems to happen, we assume nothing is changing. But inside every battery, reactions are already in motion. The object we trust is not static or finished. It is a system slowly transforming from the moment it is first put to use. Electricity responds when demanded. Chemical energy does not. Inside a battery, reactions move forward whether the system is being used or not. Energy inside a battery exists as a chemical imbalance. That imbalance constantly pushes toward equilibrium, even when the battery appears inactive. Storing energy does not stop this process. It delays it. Control begins by slowing reactions that would otherwise proceed on their own. Time becomes an active variable inside the system. Even without use, chemical change continues quietly and cannot be paused. This is why batteries age even while sitting on shelves. Degradation progresses slowly without waiting for use or demand. The first limit of energy storage is time itself. The system begins changing the moment energy is trapped, long before it is ever used. Battery materials are not chosen to release energy quickly. They are chosen to slow reactions down until they become tolerable. Electrodes are engineered to resist their own efficiency. Faster reactions would deliver more power, but at the cost of control. Electrolytes are designed as narrow pathways, not open channels. Their role is to regulate movement, not to maximize flow. Every increase in stability reduces potential performance. Capacity, speed, and efficiency are deliberately limited to keep reactions under control. This is not a flaw or compromise added later. It is the design itself, trading raw power for predictability and survival. Making energy storage possible begins by accepting less than chemistry could deliver and designing around that loss from the start. Every chemical reaction produces heat. In batteries, heat is not a side effect, but a force that constantly challenges control. As the temperature rises, chemical reactions accelerate. The same process being restrained begins to push back against the system. Higher heat shortens lifespan long before any sudden failure appears. Aging accelerates quietly and continuously. Thermal management becomes a survival system for batteries. Cooling is engineered first, shaping every performance target that follows. Energy density is not limited by chemistry alone. It is constrained by how quickly heat can be moved away without losing control. Before batteries fail electrically, they fail thermally. Heat defines the practical boundary of what energy storage can tolerate over time. A single battery cell is manageable on its own. It can be monitored, cooled, and controlled with relative simplicity. Problems begin when cells are combined. Hundreds of identical units introduce interactions that no single cell experiences alone. As systems scale, failure is no longer an exception. It becomes an expected condition that must be planned for. Cells are physically isolated to prevent one failure from spreading to the next. Distance becomes a form of protection. This isolation reduces efficiency and density. Space is sacrificed so that failure remains local rather than systemic. What emerges is no longer a simple battery. It becomes a system designed around the expectation that some of its parts will fail. Batteries are not allowed to decide how they operate. Control is handed to an external system that constantly watches for deviation. Voltage, current, and temperature are measured continuously. Every parameter exists inside a narrow, enforced range. Upper and lower limits are enforced without negotiation. When thresholds are crossed, operation is reduced or stopped. Charging rarely reaches full capacity, and discharge stops while energy remains inside the battery. Limits are enforced before stress accumulates. These limits are not inefficiencies or wasted potential. They are deliberate design choices made to preserve stability across thousands of cycles. Longevity is chosen over completeness. The system survives by refusing to use everything it could every time it operates. Every charge cycle leaves microscopic damage behind. Bonds break, materials shift, and the system never fully returns to its original state. This damage accumulates in predictable ways over time. Aging follows patterns that engineers can anticipate, measure, and design around. Degradation is not prevented or eliminated. It is actively managed, paced, and steered away from sudden and uncontrollable failure. Capacity loss becomes an accepted outcome of operation. Stability is preserved by allowing performance to decline slowly and unevenly. Sudden collapse is avoided by designing for gradual change. Aging becomes a controlled process rather than an unexpected event. Failure is slowed on purpose. The system continues to work because it is allowed to wear out in ways engineers can predict. Scaling a battery does not scale safety evenly. As systems grow larger, the consequences of failure increase faster than capacity. More stored energy brings more heat and internal stress. Potential reactions grow harder to control as limits are approached. Fire risk grows faster than energy capacity. As systems scale, protection layers multiply to contain consequences. Each added layer of protection adds complexity. Simplicity is lost as systems become larger and more dependent on control. At scale, control replaces efficiency as the primary design goal. Managing risk becomes more important than maximizing output. What grows with scale is not only power, but dependence on systems that must constantly monitor and protect themselves from their own limits. Modern infrastructure increasingly depends on stored energy. Batteries move from backup components to central pillars of daily operation. This dependence shifts where risk is concentrated. Failure no longer occurs at the edge, but inside the system itself. As reliability improves, failures become rarer. But when they occur, their impact spreads across connected systems. Risk is reduced through constant monitoring, maintenance, and human oversight. Safety becomes an ongoing process, not a fixed state. When monitoring stops, protection weakens immediately. The system remains safe only while attention, maintenance, and oversight continue. Dependency does not remove risk from the system. It reorganizes risk around components that can never be left unattended. Battery performance declines even when systems are carefully controlled. Degradation continues under normal use, following time rather than demand. Materials change regardless of optimization. Chemical structures shift slowly, independent of software, sensors, or control logic. Replacement is not a failure of design. It is an expected outcome built into how batteries are engineered to survive. Energy storage buys time, not permanence. Every battery system is designed with an endpoint already accepted from the beginning. Progress in batteries is measured by slower decline, not by elimination of limits. Improvement means extending useful life. Time remains the final constraint for energy storage. Technology succeeds only by learning how to operate within it, not escape it. Batteries do not store energy freely. They restrain it temporarily, under conditions defined by materials, heat, and time. Their limits shape how modern systems behave. What can be stored, how long it lasts, and how safely it can be used are all consequences of those limits. Energy becomes usable not when limits are removed, but when failure is slowed enough for systems to endure.